right. Exercise 1 from chapter 3. It's been too long since we've used a calculator. Let's get back into it. So exercise 1, the average mass of an element. So when we talked about the average mass of an element, it's a weighted average. So we take into consideration the percentage abundance of that particular isotope when we actually do our average mass. So this is how we would do it. When a sample of natural copper is vaporized and injected into a mass spectrometer, so we just described, the results shown in the figure, this bad boy, are obtained. Use these data to calculate the average mass of natural copper. So what am I doing? Calculate the average mass of natural copper. The mass values for copper 63 and copper 65 are 62.93 AMU and 64.93 AMU respectively. Now, if you are thinking back to this page and thinking, but you said I have massive whole numbers. You're right. There actually is a little bit of loss of mass due to a mass defect during nuclear fusion and the formation of these elements. But that's close enough. That's close enough. So, mass number is 63. That is copper 63. And so, as I read this, and do I know what do these add up to? 100%. Okay, these add up to 100%. So what we can tell from this graph is that copper has two isotopes. There's copper 63 and copper 65. Right? Those are the only two isotopes because the percentages of each of them add up to 100%. The other nice thing is when we look at the y-axis, the relative number of atoms is 100. So these become really, really nice. I mean, they're just nice percentages, right? 69.09% of all copper is copper 63. 30.91% of all copper is copper 65. It's pretty cool. But we are supposed to calculate the average mass of natural copper. Now you can say, oh, Mr. Johnson, I have a periodic table. I could just look it up. It's 63.55. Well, that's not what the question asks you to do. It asks you to calculate the average mass. Looking it up on a periodic table is not calculating. All right? Now, this is a type of question that could appear on the AP exam, most certainly. And what it's doing is it's simply assessing your basic statistical analysis as well as your ability to interpret figures, interpret graphs. Okay, and that's fair game. That's fair game. So how would we do this? Well, I know that 69.09% of all copper has a mass of 62.93. So if I'm going to take this into account and weight this, I would go 0.6909 times 62.93. So this is going to be the mass of this total sample that is due to this copper. I'm going to do the same thing with the other kind. And let's calculate. Let's see what's going on. Get my calculator app. 0.6909 times 62.93. That ends up being, let's see, how many significant figures do I want? 4. Alright, so that'll be 43.48. Okay. Let's do the other one. A little off the page. No big deal. 64.93 and get 20.07. Okay. Well, let's add those things together. Boop. Plus. Boop. If I add these up, I get 63.56 All right, do we agree? Any calculator mistakes that I made? And so the average atomic mass of copper is 63.55 AMU per atom. Now it's not grams per mole because we're calculating the average mass of a copper atom, right? And the units for the individual masses is in AMU. And so I definitely want to use AMU in my units in my response. Now, if you're doing a little bit of a longer problem, especially one that has more than 2 isotopes, there's another way that you can plug it into your calculator. It looks something like this. So what I'd do is I'd put parentheses. I'd do quantity, right? Parentheses, each of these, and then just add them together in the same line. So I would plug into my calculator something like this. Parentheses, and then add. .93, and then I'd plug that into my calculator, and it should end up being the same thing. So let's see. Parentheses. Whoop! Already messed up plugging it in. All right, parentheses plus another parentheses. 30.91 times, what's that, 64.93 in parentheses. Boom, there's my 63.55 AMU per atom of copper.